My name is Danielle Wood. It's my pleasure and honor to share this address with you in honor of your wonderful conference. I lead the Space-Enabled Research Group at the MIT Media Lab, and my title today is asking, can we map the links between nature, humans, policies, and technologies to inform sustainable decision-making? I'll share examples from several projects in my team where we try to bring this into reality. I start with the land acknowledgement, the one that we use here at my university at MIT. MIT acknowledges indigenous peoples as traditional stewards of the land and the enduring relationship that exists between them and their traditional territories. The land on which I'm sitting right now, where MIT is located, is traditional unceded territory of the Wampanoag Nation. We acknowledge the painful history of genocide and forced occupation of their territory, and we honor and respect the many diverse indigenous people linked to the land on which I'm currently sitting from time immemorial. I encourage you to explore the history of the geography of your land and consider the impacts on indigenous peoples in your area. Those in the North American region can use whos.land to explore further the names and histories of the peoples linked to your land. At the Space-Enabled Research Group at the MIT Media Lab, we seek a mission of advancing justice in Earth's complex systems using designs enabled by space. This partly means that we're asking how we can help enable a more sustainable future using technology from space to support sustainability on Earth, but also exploring the actual impacts of human behavior in space and how we can be more sustainable there as well. So our vision includes trying to design or redesign existing space technologies in support of economic, social, and environmental sustainability. This includes heavily using satellite Earth observation, satellite positioning, and the benefits of positioning, navigation, and timing technologies, as well as satellite communication. And beyond the satellite realm, we also explore the applications of knowledge gained through human spaceflight, microgravity research, technology transfer, and broader fundamental space research. And we look for ways that all these activities can contribute to sustainability on Earth and wherever humans go in space. Our vision is also to be a community that employs a variety of research methods, including these 6 at least, and as well as others. And we seek how we can apply them to support sustainability on Earth and in space. So we draw from design thinking. In particular, I highlight examples from engineering-oriented design, but it also links from other fields. We work with practicing artists or practice art ourselves, and we read heavily and collaborate with social scientists. We develop tools based on complex system modeling, and we are innovating in the area of satellite engineering. But we are also today, I'll highlight examples of our work using geographic information, artificial intelligence, and other forms of data science. So we try to answer questions frequently using maps. Our work is guided by a broad vision of what it means to make progress toward a better society. And this has been influenced by reading heavily from social scientists, artists, thinkers, especially Black women who are asking how we can advance from equity towards sustainability. Here you see examples of the types of writers that have influenced my definitions for a more sustainable society, starting with eliminating sources of disequity, especially those linked around identity that have caused people from particular groups, including class groups, income groups, racial groups, to be treated negatively. Then we can ask the question, how can we advance the liberation and self-determination of people, especially those traditionally experiencing oppression, and eventually foster solidarity among different groups, all as we work toward a more economic, social, and environmental sustainable world at both the local and complex global scales. So this, of course, is not a simple recipe, but talks about the kinds of scales of change you want to make. And the examples I'll show here mainly look at examples of local leaders trying to address traditional forms of oppression and environmental challenges at the scale of a city or a town. The work in our team addresses 3 themes. Today, I'll highlight examples in theme number 1, designing space technology to support sustainable development. But our work also includes innovating to design new space systems that are accessible and sustainable. One of our favorite examples is that we're trying to develop the use of beeswax as a propellant for small satellites. So that's a work you can see in different talks, but it highlights the opportunity to draw from sustainable sources to help space activity be more impactful in a positive way on the environment. The final example is that we explore the link between technology and justice. And in other work, we explore this through social science theory development. But today we'll focus on example number 1, and we try to, of course, take the lessons from examples 2 and 3 in that work as well. Our work is often informed and motivated by the global consensus around sustainable development goals. This is a useful set of tools, including the objectives and the targets, and the idea that there's been such consensus built around these being priority activities between now and 2030. I'm sure many of you have explored the question how geographic information can help explore both the ability to better monitor progress toward the goals, as well as information to help make decisions and manage toward the goals. So we're interested in both those areas. In particular, we like to ask, how can information drawn from satellite-based Earth observation and other geospatial sensing systems be contributing to the monitoring and management of sustainable development goals? In my work most recently, I've noticed that SDG number 15 and a few others like 11 and 3 and 6 really are well positioned to be addressed by information from satellites. It's an interesting time in the history of satellite Earth observation. I used to work for NASA's Earth science community, so I'm highlighting here examples of NASA's Earth-oriented satellites. And these are just some of the powerful scientific satellites that are available. And for those who spend less time with the science satellites, just one of the fun things to highlight is how much each mission is unique and addresses a particular measurement, what's happening in the atmosphere, on the land, in the ice caps, north and south poles, as well as what's happening in fresh water. And it's really a unique set of data that often requires deep scientific expertise to use effectively. So a lot of my work is collaborating with the scientists who are experts in these different areas to understand how to apply this excellent science material for use in decision-making. Now, there's a variety of traditions in how we build satellites, and there's one category that tries to build larger scale satellites that operate effectively for many years, maybe a decade or more, and carry multiple instruments that take measurements of the environment. We're also seeing a movement toward what's called the small satellite engineering style, which makes actually smaller satellites, but also has a vision to have simplified designs that can operate for shorter periods, perhaps in larger groups, like you see in the example of the company Planet. And some of you probably are already users of the data. So this gives us now regular revisit of information with an optical-based view, meaning pictures of the Earth the way that our eyes would see it, with red and green and blue and near infrared bands. And we get information more often. They're aiming for daily revisit of everywhere on Earth. And we also get it, in this case, with resolutions of, say, 3 meters. Other companies are offering other resolutions. So the question is, what's the best way to combine high-quality scientific data with commercially available, more frequently repeated data to get the information we need? One of the techniques, it talks about this workflow, which I draw from collaboration with scholars at NASA. They try to describe what happens when you go from having a sensor on a satellite or an airborne platform like a drone or a high altitude balloon, and take that information, calibrate it and validate it, and ultimately put it into models and decision tools that can help inform decision makers who may or may not be experts in the original data sets. And one of the great realities is that there are many steps in this value chain. In the United States, we see a lot of investment by the federal government through NASA and NOAA and the United States Geological Survey to do steps 1 through 5 to operate satellites and to provide steps toward the research that helps with the calibration, the validation, and the insertion of high quality data in public databases. And there's also an opportunity for private sector roles, especially in steps 6, 7, and 8, to transform publicly available data sets into information tools that answer questions for people who are not focused on science, but are trying to address societal challenges. I used to work for NASA's Applied Sciences program, and as one example, they have portfolios for projects in areas such as disaster response, as well as water resource management, agriculture, public health, and biodiversity and ecological forecasting. So they have the goal to explore how this diverse set of data about the environment can be transformed into information and combined with data that is socioeconomic, as well as coming from other topics such as asking how we can use a non-geographic data in the same data sets. So I'll highlight some projects where our team takes this philosophy and tries to work through parts of this value chain, but we collaborate with leaders who are trying to address a particular sustainable development goal in their community. We do this through a framework we call EVDT. It stands for Environment, Vulnerability, Decision, Technology. EVDT is a series of questions and a step-by-step process for combining information from different disciplines. The environmental modeling and analysis tends to bring in satellite data or data from other geospatial platforms, opportunities to bring data from the airborne and in situ sensors as well. And we're asking if we can describe the state of the environment, especially what's happening with vegetation, with what's happening in the atmosphere or water resources. The second piece on vulnerability asks what benefits or cost humans experience due to environmental changes. And this can be done directly looking at changes in socioeconomic variables or trying to develop risk indices to understand opportunities for change for the human side. This includes both humans, but also human infrastructure. The human decision-making model considers policies put in place by authority figures like governments or actions taken by the public to respond to changes in the environment and creates a feedback opportunity to see how human behavior changes the environmental state. The T part in the EVDT gives us an opportunity to either ask, are the technologies currently available meeting the information needs of human decision makers? And if not, what next steps are needed to further clarify this and to provide opportunities to improve access to technological sensing, which might mean designing a new satellite or aerial-based platform or an instrument for making measurements, or it might just mean collecting what's available from new sources by buying or negotiating access to new data sets. I'll show you a few examples where we put EVDT into practice, and we do it by taking questions posed by local leaders of geographic questions that are affecting local sustainability. The first example comes from Lake Nokwe in Benin, and will particularly highlight the work of the company called Greenkeeper Africa, which invited me and my team to collaborate with them on questions around a decision support tool to support integrated water resource management and biodiversity in the lake. We'll focus on the questions of managing an invasive plant. This is SDG 15.8. You're seeing some of our collaboration here. Overall, we're interested in creating a website that can be used long-term by this company called Greenkeeper Africa, which is based and founded in Benin. And you see that we're trying to ask how to combine information drawn from field work, from satellite-based data, from aerial sensors, and from in situ sensors, all in service of creating an information system that helps to explore both environmental and social impacts of this plant called water hyacinth. The ultimate goal is that we have this work in progress toward creating this information system, which will be a website that in the future will be publicly available. Right now it's under development. And you're seeing, for example, that's going to show information from satellite-based observation of this vegetation over water, but eventually will also show how the company is engaging with local people, and they have been doing for several years, who are harvesting the plant manually and helping the company transfer it into a product that can be used to absorb oil-based pollution. Some of our methodology for collaborating with the local leaders there in Benin has been highlighted recently in this paper in the Frontiers in Climate journal. The title is Inclusive Design of Earth Observation Decision Support Systems for Environmental Governance, a case study of Lake Nokwe. I want to appreciate the lead author, Ufoma Oviemira, a doctoral student in my team, and also our collaborator, Dr. Philip Muftau of the company, Greenkeeper Africa. Please check out the paper, which explains further both the ethics and the structured system engineering methods we took in order to make sure we're collaborating in an ethical way with local partners. To give ourselves some structure, we follow a system architecture framework as we're implementing this EVDT approach. meaning we ask questions around stakeholders and context before we start to design a hardware or software system. This is a summary of system architecture. It's a series of steps that are good design practice. First, understanding and asking questions around what's the physical and social context where we're going to implement a new project? Who are the stakeholders? Who have decision-making power? And who are the stakeholders who receive the impacts of those decisions? I try to understand the desired outcomes of the tertiary stakeholders, those who are going to be beneficiaries of the ultimate design. And we work closely with the local partners to decide what functional tools should we create through this website and information system, and what kind of forms, what kind of designs and actual organizations, physical tools, and people need to be put in place. This is a picture of our colleagues at Greenkeeper Africa, and particularly before COVID, we were able to do regular visits to coordinate with them and to exchange methodologies. They would teach us about their local environment, and we would work together to identify the requirements for an information system, both an online system, but also tools to put in place local sensors and airborne sensing technologies to help them organize information about the state of Lake Nokwe, to understand how it's influencing the growth of this important plant called the water hyacinth. Now, Lake Nukwe is a very interesting location where many people live in traditional modes using human-powered boats and living in homes that are physically built on stilts over the lake. So human-powered boat transportation is really key to their daily economic activity, including access to marketplaces, to buy and sell food, as well as to access clean water. Now, when you travel through this area, you're often impeded by the heavy growth of the invasive water hyacinth plant. I took this video sitting on the front of a boat, which is moving through with a motor. And thanks to the motor, we're able to eventually clear this area of water hyacinth. But those who are using human-powered transportation can often be stifled. And actually, those who are on these narrow riverways can be blocked in their water-based transport, sometimes for weeks during the major blooming of the water hyacinth plant in seasonal areas, particularly in the months of November to January. But actually, I've been there in other months throughout the year and seen large blooms of the water hyacinth. As you can see, the kinds of boats that need to traverse this area depend heavily on a clear waterway. Now, we've developed a technique, and I want to particularly appreciate Ufumo Ovimura, who I mentioned earlier, looking at ways to use existing publicly available satellite data to create an algorithm to estimate the location of the water hyacinth over Lake Nokwe. And this is important because, of course, there's many types of water plants, but the water hyacinth has particular growing patterns. So we're implementing both analysis of Landsat-based data, as well as looking at change detection approaches that match the seasonal behavior and dynamics of the water hyacinth. We can estimate which plants are water hyacinth and which are local plants that have different growing patterns and are less likely to be floating across the water. The water hyacinth uniquely grows in bunches that float together and move differently from the other plants. With this approach, we think we have pretty high confidence that we're seeing, actually using Landsat data, the abundance of water hyacinth on the lake. And we've started to then estimate the behavior over long time periods. One question that our local colleagues had was asking, has there indeed been an increase that can be quantitatively confirmed in the amount, like the area of lake covered by water hyacinth in the last few years? And you can get long-term resources of the NASA satellite data, particularly on Google Earth Engine, as many of you may also do. It's much faster than to combine a large number of data sets and run a common algorithm over multiple decades of data. So this looks at available scenes that have cloud-free data using Landsat in this particular region over Lake Nokwe. And we can then estimate the percent anomaly, meaning the level of difference across the average percent of area coverage of the Lake Nokwe with water hyacinth, and to indeed infer that the areas above this red line at 0 are areas that are, or it's a year in which you're seeing growth above average, considering this 20-year time period. So it helps us confirm that indeed, in the time between 2000 and 2020, there has been a quantitatively confirmed increase in the amount of area that the water hyacinth is covering in Lake Nokwe. And now we can ask the question, what kind of human behavior might be influencing this? From local research, we also identify evidence that the water hyacinth growth is influenced by the salt level, as well as the nutrient load in the water. And this is influenced by human waste management. and the fact that people are putting both human waste and other forms of waste into the water, but also they're putting other kinds of materials, including plant matter. In order to understand if our analysis using Landsat is correct, we did several types of validation. So as an example, comparing the estimate of the extent of water hyacinth coverage in 2 different years, 1 year in 2019, using data from both Landsat and Sentinel. And this slide gives an example highlighting the various data sources we were able to use coming from particular satellites, from local ground-based data collection, and from airborne collection. And that gave us more confidence that we could be confident about our methodology using the Landsat data. Here's another example comparing the water hyacinth classification using Landsat and the commercially available Planet dataset as a comparison. Next piece we want to add then is to respond to the fact that the water hyacinth growth does vary, and partly due to the level of salt and also the temperature and oxygen level in the water. And we want to give Greenkeeper Africa a long-term capability to make regular measurements of the in situ status of the lake. And so this means developing a low-cost sensor kit that can be maintained locally and operated by the local team. So we've gone through several iterations of designs for sensors, including oxygen, temperature, and also salt sensors. And so here we're showing the evolution of the design process and some of the testing that was done on site, as well as comparing with commercially available sensing systems. We are so pleased to see that our colleagues from Greenkeeper Africa have also developed a housing to maintain the salt and oxygen and temperature sensors, and it is powered by a solar panel and designed to transfer the data directly via the mobile network locally into an online platform on the internet to save the information in an online database. We hope to then expand to have more copies of this type of sensing system going forward. Another feature of the lake is that local people use local branches and other forms of tools to create fishing areas that are meant to help increase the catch of fish by helping to concentrate fish in areas that have protection to grow their eggs. So this practice is called a kaja locally, and it also influences the water quality because what you see is the use of these plant materials, but after they're finished, they can often be left in the water, and that leads to a decay of the plant materials, which also affects the health of the water. So this is another area we'd like to understand and try to map. And so in this example, we're now considering the use of both optical and also radar data as a way to estimate the coverage of the lake with this kind of activity of the fishing ponds. So you're seeing in this example an estimate where we're estimating categorizing the pixels and which ones seem to include this akaja. And what you're seeing is the areas that seem to have these geometric shapes that are human-oriented shapes are high likelihood to be akaja. So all in all, we hope to eventually compile the information drawn from airborne sensing through drone operations of cameras and water-based sensing of temperature, oxygen, and salt levels. And of course, also looking at satellite-based sensing of the presence of both the akaja and the water hyacinth, all into an information system. The information system also will include locations where local villagers are contracted to collect the water hyacinth and identify what they're collecting. And this comes together as an information system to both celebrate and plan Greenkeeper Africa operations in the region. This is an example of an integrated information system that uses information about the environment and human decision-making. So it particularly highlights the E and the D in our EVDT framework. Another direction comes from our work in Ghana, also funded by NASA's Applied Sciences program, and we're analyzing the deforestation due to mining in Southwestern Ghana. I want to appreciate our collaborators at the Ghana Space Science and Technology Institute, as well as the Ghana Statistical Service. I also appreciate that there are regional teams, especially at the CERGIS, the Center for Remote Sensing and GIS, doing very related work that we've collaborated with and compared with along the way. NASA's SERVIR program is also heavily involved with this topic. The entire government of Ghana has been concerned about the question of how to manage deforestation due to small-scale mining and mining that does not follow the local requirements with regard to protecting the environment. In this example, you see me interacting with our colleagues at the Ghana Space Science and Technology Institute, considering different methods for reducing the error as we use geographic analysis to estimate the location of deforestation due to mining. We recently published in Science of the Total Environment a paper called The Large Footprint of Small-Scale Artisanal Gold Mining in Ghana. I want to appreciate our collaborators from NASA, as well as from East Carolina University, and of course from the institutions in Ghana. The paper goes into more detail, highlighting our methodologies using primarily Landsat data, but also several other data types. You can see some examples here. We're drawing from Landsat for the more visual information, but we also were interested in elevation data, drawing from Tandem X and from digital elevation models. So this helps us ask the question, first, what types of mines are we seeing in Southwest Ghana? Some are large-scale mines that are industrial scale. Some are the smaller ones that are using techniques that are often not approved in terms of protecting the environment and managing water pollution. We're drawing from the data from Landsat to estimate what kind of land use classes we're seeing and dividing the land into different categories, including vegetation and urban and water. And then we're looking for areas that have changed land use class and identifying the ones that are highly likely to be mining impact. And this process is detailed further in the paper by Barenblatt et al. We were able to develop a time-based analysis to see in which years there was transformation of vegetation into areas that had high likelihood to be mining. And as you can see, in the period between 2013 and 2017, there's an increase in the rate of transformation of vegetation into mining areas. There's also some transformation into urban use. So it's another category that we tracked as part of our land use change analysis. And this makes heavy use of the Landsat 7 and 8 imagery. Here's an example looking at a section in Southwestern Ghana, highlighting a particular time snapshot where we identify different land use classes, including mining, both small scale and large scale, as well as urban and water. And these are areas that are particularly relevant to the question of where are there rivers that are being affected by mining, and where is their transition of vegetation into urban areas. So in particular, the mines at the smaller scale in yellow were our key analysis topic. This also allows us to do a time-based analysis to see at what year the transition was made from vegetation into mining. And we see some of the areas, particularly gradually kind of moving from the river itself out and away from the water and having additional mining over the years between 2007 and 2017. One question we also asked is whether the mining was happening inside areas that are a zone for protection. So the boundaries you see here in pink represent protected areas coming from a world database for protected areas. And we were asking the question whether the small scale mining you see in yellow is happening equally inside protected areas or also more so outside. And we see some overlap where sometimes inside the area that's labeled protected, there's still additional deforestation due to mining. This work also involved accuracy assessment, in particular identifying points that were reviewed using high-resolution satellite data because our technique involved developing a machine learning algorithm to classify the different land use cases. So to spot check that, we chose some areas and manually checked them using high-resolution data to then get a better sense of the accuracy of our machine learning algorithm. This information is available to you because we've created a web map in Google Earth Engine that's publicly shared. And if you search for the paper, you can find links to the web map as well. And it gives a chance for someone to explore our data in an interactive way and zoom in to see the areas and the years of transition from forestry into mining in a very accessible platform. As we think about the projects in Ghana and in Benin, I also want to reference Jack Reed, who is one of the doctoral students in my team, all the way on the left of this photo. And Jack is shown here pre-pandemic with collaborators in Rio de Janeiro. And Jack is one of the key researchers using our EVDT framework, Environment, Vulnerability, Decision Technology. In this application, we're applying it to examples in Rio de Janeiro. In the background, you see the growth of mangrove trees, one of the key trees that's vital for coastal resilience in local areas where the mangrove is native. And the mangrove plays a role in helping to ensure that we have access to healthy coasts with fish habitats, as well as protecting the coastline from erosion. So Jack had been working for several years, focused on the topic of thinking about the mapping of the health of mangroves and asking how the city government of Rio de Janeiro is enforcing land use and land management practices to keep the mangroves healthy, but also considering the needs of local fishers and other community members for short-term use of the wood from the mangroves, and the question of how city management supports the health of local fisher economies. The team here you're seeing is from the Federal University of Rio de Janeiro. They are local collaborators who are also engaged in related research. This is one environment where we're applying the EVDT framework, where the satellite data is helping us estimate the state of the mangrove trees, and then the vulnerability pieces bring in information into an information system that Jack's developing, considering the demographics and economic well-being of the people living near mangroves. In particular, we have funding from NASA and from the Research for the Future consortium on, it's called Valuables, a piece that asks what's the value of having satellite-based elevation data for socioeconomic analysis. And through this project, we're working with Professor Seyoung Jun of West Virginia University to develop economic analyses considering this region of the mangroves and the nearby regions, and then comparing how conservation of the mangroves and observation of the mangroves using satellite data is relating to the well-being and economic wealth in households nearby. These are all examples of applying EVDT, and I want to note that when COVID came, we asked the question, can the same techniques be applied in a way that's relevant to public health? So we introduced the VITA decision support system, and it takes the same logic of EVDT and now applies it, including a public health component. So you see we still have environmental models, socioeconomic models, decision models, and technology models. And we then implemented a new approach by drawing from collaboration with those who think about public health modeling, particularly the SEER, the susceptibility, exposed, infected recovery model, which we can then add as a piece to our bigger picture. So Jack actually had been working in Rio de Janeiro and then thought about applying that same approach and helped us start this team to build a broader tool with multiple collaborators, both in the United States and also abroad. So Jack is going to share a bit in his own words now through a video he's created about VITA and our decision support system that builds on EVDT, but applies it for COVID.
Human impact and vulnerability, decision-making, and technology. You can see these components here in the default arrangement, aimed at answering 4 basic questions. What is happening in the natural environment? How will humans be impacted by what is happening in the natural environment? What decisions are humans making in response to environmental factors and why? What technology system can be designed to provide high-quality information that supports human decision-making? Pre-pandemic, we applied this framework to several different applications, some of which are shown here. All of these were firmly in the sustainable development domain with a strong environmental component. Depending on the application and the intended goal, the components of EVDT can be arranged in different ways. Here you can see one version for informing policy design and another for informing technology design, specifically remote observation system design. In diagram A, the primary loop is between decision-making, environment, and social impact, with technology merely providing data to inform the user. In diagram B, the primary loop is refining the remote observation system design by examining the impacts of different designs on the environment and human society. When the pandemic began, the priorities of many of our international collaborators shifted, naturally enough, and so we too shifted to providing coronavirus-related support, as embodied in the VITA decision support system. For this, we broke out public health as a separate component in order to make it the primary focus of the system. Ultimately, we ended up collaborating with teams based in 6 locations across 4 different continents, focusing on several major metropolitan areas. These teams involved a mix of government officials and university researchers. The primary collaborators would bring in additional people as needed. The US team has one-on-one meetings with these international teams on a weekly or bi-weekly schedule. We also conduct monthly full network meetings, where where collaboration participants can present and discuss relevant topics, such as how to integrate wastewater treatment data into decision-making, how to include health surveillance in elderly care facilities, and how to identify high vulnerability neighborhoods. We also conduct collaboration online via our collaborators' own data repositories, the GitHub repositories of the VITA code, and a browser-based version of VITA that I will be showing later. In short, our collaborators are involved at every stage of an iterative process, informing both the initial system architecture and ongoing development, including directing the topics of investigation. Moving into data and methods, I will briefly go into each of the 5 components of VITA, summarizing our primary data sources and some of the techniques we use for analysis. Regarding those methods of analysis, more detail is available in our other presentations and publications. Starting with public health, we rely predominantly on data collected by local public health authorities. These are typically available on a daily or weekly basis. These datasets are then used in a susceptible, exposed, infected, recovered, or SEER epidemiological model built using system dynamics. This model integrates several aspects of other VITA components, including weather and pollution. The current version is non-spatial, though for some applications, like the Indonesian islands of Java and Sulawesi, we run separate versions for each distinct area. This model is being refined and expanded based both on increased epidemiological information and on findings from the other VITA components, which I will describe shortly. For the environment, we monitor air quality and water quality from remote observation, with air quality being supplemented by hourly in-situ monitoring in the Rio and Santiago locations. We also track nightlights using some of the newer VIRS datasets, as this provides insight into human movement and activity in urban areas. Here in Rio de Janeiro, for instance, you can see that in the initial weeks of the pandemic, the coastal downtown districts, airports, and tourist areas markedly darkened, while the mixed-use and residential areas brightened. Similar results hold for our other locations, often even more starkly, as can be seen in this comparison of Rio de Janeiro and Bali. With air quality, meanwhile, we have seen smaller changes, particularly once seasonal and long-term trends are taken into account. Work is ongoing on this front, however, so our results may change. On the vulnerability side, we use both socioeconomic data, such as poverty and employment rates, and mobility data. The former tends to only be updated monthly or quarterly, while the latter tends to be available much closer to real time. The mobility data itself takes a variety of forms, and we are working on seeing if we can correlate the mobility data with nightlight data. In general, however, mobility tends to follow a combination of policy changes and COVID-19 caseloads, but tends to rebound towards pre-pandemic norms, even in advance of loosening policy restrictions. This graph shows the Metropolitana region of Chile over the course of the first year of the pandemic. We see similar results over the other regions, though with different holidays and political events. For decision-making, we focus on social distancing requirements and public area closures or restrictions. Obviously, we rely upon announcements from local authorities, some of which are connected to well-defined staged policy systems with conditions for advancing or retreating among the stages. We are also actively working to try and conduct more quantitative policy comparisons across locations using such datasets as the CoronaNet research project. On the technology side, as was made clear a few slides ago, Earth observation systems are still highly relevant with expanded uses. Another key sensing technology that we have been collecting use data on has been coronavirus testing data, both those aimed at identifying active infections and antibody tests. All of this comes together in the user interface, which has 2 versions. The one shown here is a desktop version, which has both data visualization and simulation capability. This is using Rio de Janeiro as an example. The simulation can either be run manually by inputting specific policies and moving forward a week at a time, or autonomously according to various pre-coded decision rules that can be made to match those of the actual government authorities, as the case may be. The UI can shift between different languages, locations, and layouts according to the needs of our international collaborators. The online version, meanwhile, focuses on data visualization, here showing parts of New England. Once again, temporal data is shown on the left by default, while spatial data is shown on the right. Moving forward, we are continuing work on several fronts. Some of these are about improving the usability and accessibility of the decision support system user interface, while others are about investigating new data analysis and simulation methods to determine their utility. I will close there and encourage anyone who is interested to reach out to us.
Big appreciation to Jack for making that excellent summary of the Beta Decision Support System. And you can learn more about that at our website at spaceenabled.media.mit.edu. As you can see, we're often exploring how to bring together data about the environment, human vulnerability or societal positive impacts, human decision-making, and the use of technology to observe the environment. We're often asking how we can apply this for locally driven or regionally driven questions, including how to manage the health of mangroves, other forests, and invasive plants, as well as how to respond during crises like COVID. One of our key guidelines is to apply EVD&T in a setting where we're using systems thinking as guided by local hosts who have clear research questions and policy questions to answer. We hope that these examples are relevant to your work, and you may find ways to use similar work and share your findings with us as well in the future. Thank you so much. It's my pleasure to work with you. I look forward to future conversations. Thank you.